Hi guys. Okay, so it's just about an hour before your class starts. I'll see if I can run a quick introduction to the DSC and TGA behind me and get it loaded before class starts. I guess if you're watching this, I succeeded. Okay, so this is a DSC and this is a TGA. TGA looks like a cappuccino machine, but it doesn't make cappuccino. If it did, it would be really tiny cappuccinos. That's a joke based on the fact that the cups that you use for these tests are that big. So that's the little cup that we use to put samples into for both of these machines, and you can see that they're just absolutely tiny. They take like a 15 milligram sample. Typically, you can put larger samples in, and in fact, we're going to do a calibration run on this DSC using a sample that's up around 250 milligrams or so. Okay, so the calibration run that I'll do is just a nice, easy way to demonstrate the functionality of the machine. And to do it, I'm going to use one calibration material that I have here called indium. And the two numbers indicated are the transition temperature when it melts, and also the enthalpy of fusion, so the amount of energy required to melt it, and that's given in joules per gram. Okay, and so when you get these machines, you need to have a few calibration materials, and it's helpful to have those materials be at several different temperatures and enthalpies of vapor of fusion, so that you can pick up the whole range of operating temperatures. So there's tin, that's at 232 degrees C, and here is zinc at 419 degrees C. So we'll do indium, and there's just a couple pieces in this little bottle, and one of them will get placed into this cup. So there's my sample. You can see it's really tiny, but that's about 20 times as large as an average sample for a DSC or a TGA test. It gets placed in that little cup, and then I'll bring the camera over and show you what happens next. Okay, so here's the top surface of the DSC, and what you see is the two cups that we referenced in the slides. Hopefully I talked about the slides before showing you this. And we drop that cup in there, and the other cup over here you can see is just an empty an empty container, and we do that to account for the heat flow into the container itself, so that the machine will isolate the effect of the heat flowing into the indium. In other words, it will subtract the empty cup on the right, that data, from the full cup on the left. And you can see that you typically want to put a cover on these cups, which I often don't do because I'm lazy, I guess, and you get this splattering around the outside as the thing heats up, depending on how high the temperature is. So we go ahead and cover this guy up and latch it down like this, and there's a cover for it. And I'm not going to actually run the test for you right now. Let me just put my sample away. I'm not going to run the test. I'll show you the data from a test though. So here it is, and what you see, let's see if I can get in here close enough so you can make everything out. What you see on the left is heat flow, endotherms down, meaning, there we go, endotherms down, meaning that endothermic behavior, that is heat flowing into the sample, is indicated by the curve flowing down. Okay? So that's what you're seeing here. And then down on the x-axis is temperature. So here's the question. When we ran our test, which is showing you the amount of heat flowing into the sample in milliwatts, okay? So milliwatts of energy flowing into the sample all through here, and then suddenly there's a big increase in the amount of energy flowing into the sample, right about here. And if we use one of our tools up here that says onset, we click on onset, and we grab this little X right here and move it over to sort of close to the region where we think the onset occurred. And then we grab this other guy and we move it over to sort of a region downstream, you know, kind of well downstream of where we think the onset occurred. And now ask this thing to calculate what it thinks the onset temperature is. And in this case, it has told us that it thinks the onset temperature is about 159.65. And if we look at our indium sample, we see that it's 156.6, so not bad. That's not terrible for just a quick test. And then the other thing we can calculate is, we'll go up here to calculate again, and the other thing we can calculate is called peak area. So we'll click on that, and we'll do the same thing. We'll drag our cursor over to sort of the region where we think the onset of melting started to occur, and we'll be conservative and keep it far to the left and far to the right. And let me just do that one more time because I don't think I got it done correctly. Peak area. And so we're going to move our one cursor over here, and we'll move another cursor here, and then hit calculate, and it's going to pick up the entire area in that triangle. And according to this, that area corresponds to a total energy of 6.2 joules, 6,293 millijoules. And it's done a calculation of the enthalpy of fusion for us, but I know that's not right. And the way it did that calculation was by using the mass of the sample. But in this particular case, I didn't enter the mass of the sample, so it used some old value. My sample mass was 267 milligrams. And I did this calculation and I came up with about 24 joules per gram. And our jar tells us that we're actually at about 28 and a half joules per gram. So again, not terrible, okay? So that's the way the DSC works. And I think what I'll do is stop at this point, upload this guy, and then start on the TGA.